Hello, everyone, and welcome to this beautiful session. So, finally, I'm here after so long. And if you ask me why so long, yes, there were a lot of things that I was working upon. And yes, what was it? It was all about the students, it was all about you. So, I was working on something, but soon I will be telling you what were those things. And right now, I'm coming to plan with the videos. Okay, I'm planning to come with some videos which is going to benefit the students who are writing IBDP, IBMYP, IGCSE, and also A and A level examinations, right? So in my every video, I'll be solving some questions, and I will be telling the students how the thought process should be and how to apply physics and what goes wrong with most of the students when they are writing any physics examination or doing any physics questions, right? So let's begin. So today I'm here with an IBDP question. It's a paper 2 style question, and it's from electromagnetic induction. And as you can see here, you have a magnetic field and you have a coil which is rotating with a certain velocity, I mean the angular velocity. So let us get into this question and answer. Define magnetic flux and write its expression in terms of magnetic field A and magnetic field B and area A. So we very well know that we have a formula which tells me this. Okay, we have a formula that talks about magnetic flux, right? And that formula is flux is equal to area, sorry, magnetic field, area, and cos theta. Magnetic field, area, and cos theta, where B is the magnetic field, A is the area of cross section of the loop. So you know that we have a loop that rotates in the magnetic field. A loop is a closed wire, and any closed wire is going to form an area because that closed wire is forms in perimeter, and that perimeter encloses one area. So that particular area we are talking about here. And of course we have magnetic field is B, area of that closed loop, and theta is the angle between B and A, the magnetic field and the area. So this is the expression for the magnetic flux. One marker, a simple question. Then we have part B. The coil rotates in a uniform magnetic field. Starting from the expression, see the answer is given here. Phi is equal to BA cos theta. Derive an expression for the instantaneous induced EMF, showing each logical step very clearly. And yes, there is something, there is a curiosity trigger in this question. That's why I have showed a curiosity trigger and a surprising compact relationship that you are going to get in this particular question. That's why a small mention has been given here. So to begin from here, now you have to understand that DP questions, the answers, you might have to derive few things. Small derivations do come, just like CBSE. In CBSE also you have a lot of derivation based question, but unlike CBSE, these questions are much more kind of smarter. These derivations are much more smarter. Now let's begin with this particular uh, thing. BA cos theta. Okay, BA cos theta. Phi is equal to BA cos theta. Now understand that you know that the Faraday's law says that the EMF is equal to rate of change of your EMF. Rate of change of your EMF. Eta is equal to, the EMF is equal to rate of change of a flux. Sorry, EMF is equal to rate of change of your flux. Now, yeah, of course, you will have this formula, you will have this formula. Now, what I'm going to do with here, I see I have my flux here. Now, rate of change of flux. So here what I need to do is I need to differentiate with respect to time. And when you differentiate with respect to time, where is it? Yeah, when you differentiate with respect to time, you are going to get, you see, d phi by dt. You can see here, d phi by dt is equal to b a. Now you see that magnetic field is not changing here. You see here, when your coil is rotating, when your coil is actually rotating, your magnetic field is not changing, neither your area is changing, right? but your angle keeps on changing. When a rotation happens, remember that is when your angle keeps on changing, right? So now when your angle is changing, your cos theta is going to get differentiated with respect to time. Okay, your cos theta is going to get your cos theta is going to get differentiated with respect to time, and you very well know differentiation of cos theta is sine theta. And then if you have the if you know the rule of differentiation, theta also gets differentiated, right? So technically it is b a differentiation of theta, rate of change of theta into sine theta, sine theta, rate of change of theta into the sine theta. Now you know that rate of change of theta is the angular speed. How fast the theta changes is called the angular speed. And now, so you have d phi by dt is equal to b a omega sine theta, right? Now this is the EMF produced. Now look here, students, this is the EMF produced. I told you EMF is rate of change of the flux. Okay, so this is the EMF produced, b omega a sine theta is the EMF produced. Now look very closely. Your flux is a cos function. Your EMF is a sine function. Your flux is a cos function. Your EMF is a sine function. Now understand this particular logic very clearly, because we are going to use this and understand something in the upcoming question, right? Now a coil has 120 turns, area is 0.15 meter cube, meter square. The coil, and let me zoom in a little bit. A coil has 120 turns, area is 0.101 meter square and rotates 45 radian per second at a uniform magnetic field of 0.25 Tesla. Calculate the maximum induced EMF. Now I just now showed you the EMF formula. EMF is B A omega sine theta. B A omega sine theta, right? Now understand one thing. When you have n number of turns, you just have to multiply this with n, because this EMF is produced by only one single loop. This EMF value is produced by only with one single loop. All right, now if there are n number of loop, then you just have to multiply this with n. So now the total EMF produced is n b a omega sine theta. Now this is the formula for the EMF produced by the 120 turns, n number of loops. So I have n is given, n is 120, area is given, your speed is given, radian per second is given, and magnetic field is also given. Now they're asking calculate the maximum induced EMF. Now understand one thing, it's a sign variation, it's a sine function, as you can see. So the maximum value of sine function is possible only when sine theta is 1. When theta is 90 degree, that is when you have the maximum value of sine. So your maximum value of EMF is NBA omega. NBA omega. Now all the values are given here. Now you can put it the calculation. You can put NBA omega. You can put them BA omega. You will be getting approximately, if you calculate around it, you will be getting it somewhere around 120 into 0.25 into 0.015, right? And into 45 is going to give you 20.3 volt, approximately 20.3 volt, right? So that is the answer for this particular part C. Going to the next, sketch on the same time axis one full cycle of magnetic flux through the coil and induce EMF E. The sketch must be clearly showing the phase relationship. Now in the same graph they're asking me. So let me draw a graph, let me show you how the graph will look. Let me draw a graph, an axis, which is y-axis. I have positive and negative y-axis. Now in this, first let me draw the magnetic flux. Now look at the magnetic flux formula, BA cos theta, right? Now if you are plotting a magnetic flux, okay, if you're plotting a magnetic flux for one whole cycle, when they mean one whole cycle, that means they say it's going from 0 to 360. It is going from 0 to 360. That's the meaning of one whole cycle. Now when I say one whole cycle for flux, remember it is a cos function. So cos function, it goes somewhat like this. So this is how it goes, so you will have at 90, at 90 pi by 2 it is going to be 0. Then you have a max, right? This max will be achieved at 270, right? This max will be achieved at 270, and then you go back at 360, 360. Okay, sorry, the max will be achieved at 180. Sorry, negative max will be achieved at 180. Okay, it will be achieved at 180, and from there 270 it goes here, and it goes back on full cycle at 360 at 0, it goes to maximum again. Now this is the function of flux. This is the function of flux. And let's talk about induced EMF. Now, induced EMF is a sine function. As you can see here, it's a sine function. So for one whole cycle, it is going to follow a sine function. Understand, when they're asking you to sketch the relationship, you see you are having the EMF in the y-axis, and you're having the theta or omega t or theta, of course, omega t or theta in the x-axis. So this is how you plot the first one. Now for, so sorry, this is for flux. So what you have got for flux, eta is for flux. Now in y-axis you have E, that is EMF. Now in y-axis you have EMF. Now how the EMF is going to be? EMF is going to start from 0, in 90 reaches the maximum, okay, reaches the maximum, then at 180 goes to the minimum, right? Then minus 270 reaches the negative maximum, and of course reaches 0, okay, reaches 0 at 360, right? So now this is how your EMF graph looks like. This is how your EMF graph is going to look like. So what you're understanding here is that they both have a phase difference of pi by 2, or I would say 90 degree. Their phase difference is 90 degree. Why? Because when this is starting, you see, when this EMF wave is starting, your flux waves already reached 90 degree forward. Can you see? You know, when EMF wave is starting, clearly you see, when EMF wave is starting from 0, your flux wave has already started and covered 90 degree distance or 90 degree angle. So it means that the phase difference between these two is 90 degree, right? Now going to the next question. So yeah, this is understanding of this particular question. Now going to the next question, you understand this question clearly. Explain why the induced EMF is always 90 degree out of phase with the magnetic flux. Correct the misconception that EMF should follow flux. Now, yes, I am told you the reason why. Okay, they both are having a phase difference of pi by 2. Okay, they both are having a phase difference of pi by 2. It is mandatory. Why? Because of the Faraday's law. Because of the Faraday's law. Now, Faraday's law says that your flux is BA cos theta, BA cos theta. So, flux is a theta cos function. On the other hand, the EMF is when you differentiate it, EMF becomes BA omega, see, BA omega sine theta. BA omega sine theta. So one is cos, one is sine. So you very well know that they both are having a phase difference of 90 degree. Why? Because sine, according to mathematics, sine theta is equal to cos 90 plus theta. Sine theta is equal to cos 90 plus theta. Now this is the reason why they both are having this phase difference, and this phase difference is very much mandatory. This phase difference is very much mandatory here, right? Now, do you define, now we have, right, now let's go to the part F. Define the square root, square mean, sorry, root mean square value of an AC quantity. Show for a sinusoidal voltage Vt, V naught sine omega t, the RMS value is V RMS is V naught by 2. Now what we are going to do here is, here we have a small magic of, we will doing integration here. So we know that Vt is equal to V naught sine omega t. I know that Vt is sine omega t, right? And from here, when you integrate it for the whole cycle, now of course, as I told you, the integration is required. When you integrate it for the whole cycle, you are going to integrate. So V naught will come outside. You see, the V naught will come outside. So Vt, okay, the V average. Now it becomes V average. Okay, V average is equal to V naught and integration of sine for the whole cycle. And you know that when you integrate sine for the whole cycle, you are going to get 1 by 2, because mathematically sine integration for the whole cycle from 0 to 360, sine integration gives you 1 by 2. So you have 1 by 2. So now you have V average is equal to V naught by 2. V average is V naught by 2. Now from here, I have to take the square root of it. Okay, root mean square. Root mean square. So I took the average. I took the average. Okay, so now I took the average. Now I have to take the root of it. Okay, I have to take the root of it. Of course, yeah, I just forgot to do one thing. I have to take the square here. You see, root means square. Square, V naught square, and sine square, sine square omega t is 1 by 2. Okay, the integration of sine square omega t, sine square omega t is 1 by 2. So you have again V naught square left here. Then V average of square. Okay, then V average of square is equal to V square, V naught square by 2. Now you take the root of it. Okay, take the root of it. Now that is going to give you VRMS. So it's going to be V naught by root 2. V naught by root 2. So how do you do here? Remember, root means square. So you square it. So when you square it, you have V naught sine square by omega into omega t. Then you have V square is equal to, so V average square is equal to V naught square and sine square omega t. So the average value of sine square omega t, when you integrate sine square omega t, you get 1 by 2. And from there, what you're going to get, you are going to get V square is equal to V naught square by 2. So V average square. So from there to, when you root it, so you have root mean square. Root mean square is V naught by root 2. So this is how you get this particular definition but this formula. Last one, a transformer has 150 turns on the primary coil and 900 turns on the secondary coil. 150 in the primary, 900 in secondary. The primary voltage supplied is 230 V RMS. 230 volt is RMS, is the primary voltage supplied to it. Define or determine the secondary voltage. Now for that you need to know the formula, and the formula here I would be giving you as Vs by Vp. Okay, I will give you Vs by Vp is equal to Ns by Np. Ns by Np, Ns by Np, where S is the secondary, P is the primary, right? So secondary voltage by primary voltage is equal to secondary number of turns by primary number of turns here, right? So they both are equal. Now from here I can substitute my values. So the transformer has 150 turns of primary coil. So my primary coil is 150 turns, 150. Then your primary coil 900 a secondary coil, I have 900 here, and the supplied is the primary supply is 230, so 230 is a supplied, and they are telling you to find the secondary voltage. Vs is what they're telling you to find. So from here I can get Vs is equal to 900 by 150 into 230. So when you, yeah, 230, so approximately when you're doing the calculation, you are going to get 1380 voltage. Okay, this is secondary voltage. Now the second one is a very general question. Explain why real transformers have lower output power than the ideal ones. And here the answer is none other than the loss of energy. Okay, remember, transformer is a very heavy device with heavy metals, and of course there is a lot of magnetic flux linkage going on. So there can be flux loss, there can be heat loss, there can be hysteresis loss. So there are so many things that can happen there. So these are the types of losses that happen, and because of which the input power and the output power mismatch happens, and because of that the output power does not have equal enough, the in an ideal one, your output power is always lower than your input power. So that is what happens with the transformer. Now students, so this was a big question. Yes, this is how your DP questions are. Now follow me for more questions like this. I'll come with the next video with IBMYP style questions. So I am making a lot of questions for you, and I'm solving those questions here for you for a better understanding. And you also should know how we need to do a physics question in a proper, in a right way. So with that, I will end today's session. We will see the next video. Bye, students.